Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. I welcome you all in class of real analysis. In today's lecture, we are going to start a new chapter, chapter number 2, the real numbers, from the book of Robert G. Bartle, Introduction to Real Analysis by Robert G. Bartle. In today's lecture, we will discuss section 2.1. This section consists on algebraic properties of R, the order axioms of set of real number R, some related theorems and examples, uh, arithmetic geometric mean inequality, and last one we will discuss the Bernoulli inequality. So it might be possible that to the lecture be a little bit long. So if you find any inconvenience during lecture, you can watch this lecture in different settings. Let us start from the algebraic properties of R. The algebraic properties of R are actually the axioms of field. Algebraic properties of R, set of real number R. These are actually the field axioms. From your abstract algebra, you know the set of real number R is a field. It satisfies some properties that includes the first one is commutative property. Commutative property. In the commutative property, you know, if A and B are any two real numbers, then A plus B is equal to B plus A. If we discuss the binary operation addition, and if we discuss the binary operation multiplication, then A into B is equal to B into A. Similar one, the next one is associative property. Associative property. In this property, if we have A, B, C are the three real numbers, then A plus B plus C is equal to A plus B plus C, and in case of multiplication, A into B into C is equal to A into B into C. The next one is identity elements. Identity elements. In case of addition, you know, 0 is additive identity. 0 is called the additive identity. Additive identity. For all A belong to R, 0 plus A is equal to A plus 0, which is equal to A. This shows 0 is playing its role as additive identity. Similarly, in case of multiplication, you know, one is called multiplicative identity. Multiplicative identity. That is for all A belong to R, 1 into A is equal to A into 1, which is equal to A. The fourth one is the inverse element. Inverse element. In case of addition, if the binary operation is addition, then for all A belong to R, there exists minus A belong to R such that A plus minus A plus A, this gives us the additive identity. So in this case we call A and minus A are the additive inverse of each other. And in case of multiplication, for all A belong to R, where A is non-zero, there exists a reciprocal or multiplicative inverse 1 over A in R such that A into 1 over A, 1 over A into A gives the multiplicative identity. So these are the total 8 properties. The next ninth one is distributive law. Ninth one is distributive law. Distributive laws of multiplication over addition. In this law, if we have three elements A, B, C, then A into B plus C is equal to A into B plus A into C. As we are multiplying A from the left side, that's why this is called the left distributive law. And if we multiply A from the right side, like this is called right distributive law. So the set of real number R satisfies these 9 axioms, and these 9 axioms called the axioms of the field. In some textbook, it might be possible that when you see you will find there are 11 axioms for the set for a field. Actually, Robert G. Bartle is not including explicitly Collier property or Collier law. Collier law or Collier property. In some textbooks of real analysis, the Collier law is mentioned explicitly. So if we include here the Collier law under addition and under multiplication, then we have a total 11 axioms for field. The Collier law or Collier properties for all A, B belong to R, their addition as well as their multiplication both belong to the set of real number R. So we can summarize these 11 properties into simple two sets. Set of real number R is called field. If R is abelian group under addition. Similarly, R under multiplication is an abelian group. To form an abelian group, we need 5 properties. First one is a Collier property. The second one is associative property. The third one is additive identity. The fourth one is additive inverse, and the last one is commutative property. So there are the 5 axioms for abelian group under addition. Similarly, the 5 axioms are for abelian group under multiplications, and the 11th one is distributive laws. So in that sense, you can say that to form a field, R need to 11 axioms. Okay, now I am going to start the first theorem, theorem 2.1.2. This theorem can be stated as, next we are going to discuss theorem 2.1.2. This theorem consists on the three parts. These are some basic theorems. Actually, to prove these theorems, we will use the basic properties of fields. So in the first part, we have to show that if z and a are the two real numbers, and given that z plus a is equal to a, then show that z is equal to 0. In other words, this equation is possible only when z is equal to 0, because when you put here z is equal to 0, then it is clear that a is equal to itself. But we cannot plug this value of z is equal to 0 directly here. We have to prove this by using some properties, by definitions. Here it is given that z and a both are the real numbers. As R is a field, so the inverse, additive inverse of every element exists in R. This implies if A is in R, then minus A is also belong to R. Now consider the given equation. Given z plus A is equal to A, I have to prove z is equal to 0. So to prove z is equal to 0, I will add the additive inverse of A, that is minus A, on both sides. By adding additive inverse of A, that is minus A, on both sides of the equation, this gives z plus A minus A, and I am using here the associative property also. So this becomes A plus minus A. As you know, A and minus A are the additive inverse of each other, so their sum is, the additive identity is 0. So the left side becomes z plus 0 and the right side is also 0. As 0 is the additive identity, so we can, when we add 0 to any element of R, it will not affect that element. So this gives z is equal to 0, and that completes the proof. Next one, in the second part, B, in the B part, we have to show that if U and a non-zero element B are elements of R, are elements in R, with this equation, with U into B is equal to B. This is possible when U is equal to 1. So as the first part, we will show that if this equation holds, U into B is equal to B, then the value of U is 1. Here U and non-zero element B both are the real element. This implies the reciprocal of B, 1 over B, exists in R. Now we multiply this equation by 1 over B on both sides. We have U into B into 1 over B, B into 1 over B. By using the associative property, this can be written as U into B into 1 over B As b and 1 over b both are the reciprocal of each other, this gives us 1, and this is also 1. U into 1 is equal to 1, and 1, as 1 is the multiplicative identity, so when we multiply u with 1, this gives u which is equal to 1. And here you can mention all of the axioms that I have described. This is the these are the reciprocal of each other, that's why this gives the result 1. 1 is the multiplicative identity, so their product is, this product is equal to u. In the next C part, if a is any real number, then we have to show that a into 0 is equal to 0. Okay. C part. If a belong to R, then show that a into 0 is equal to 0. We will consider the left hand side, which is a into 0. Can we write this side as a into 0 plus 0? Because 0 is a additive identity, so we can add. This will not affect any elements. Can we write 0 as a plus minus a? Further, as 1 into a is equal to a, so we replace this a by 1 into a. This gives 1 into a plus minus a. Next, by using the associative property, we have this step. By using the right distributive law, left distributive law, or by taking a as a common, you can say this is 0 plus 1 plus minus a. 0 is the additive identity, so when we add 0 to 1, this gives 1 plus minus a. A into 1, simple, this is equal to a, this is minus a. As a and minus a both are the additive inverse of each other, this is equal to 0. That is required. Okay. In the next theorem, we will discuss the two important properties of multiplication. One is the properties of reciprocal, uniqueness of reciprocal, and the second one is the product of the two number is 0 only when one of them is 0. So this is the theorem number 2.1.3. Theorem 2.1.3. In this theorem, the first part is if a is non-zero and b is a real number are such that a into b is equal to 1, then we have to show b is 1 over a. Okay. We have a given equation a into b is equal to 1. Then from this equation we have to show b is equal to 1 over a, where a is a non-zero real number. Can we write the element b as b into 1? Because 1 is a multiplicative identity, So we can multiply one with any other elements. It gives the same elements. So b is equal to b into 1. This one can be written as a into 1 over a, because 1 is a into 1 over a. By using the associative property here, we can combine these two numbers b into a, as it is given that a into b is equal to 1. So b into a is equal to also 1, because in the real number, a set of real number, commutative property hold. So this is equal to 1 into 1 over a. 1 is the multiplicative identity, so this gives us simple 1 over a. So this gives the proof of first part. In the second part, we have to show if a into b is equal to 0, then either a is equal to 0 or b is equal to 0. This is important. In the b part, we have to show if given a into b is equal to 0, then either a is 0 or b is 0. We suppose a is a non-zero, and we will show that b is 0. Okay. To prove, we suppose that a is a non-zero element, because we have to show that either one of them is 0. So we suppose a is non-zero, and we show that b is 0. For this, we multiply 1 over a with this product a into b, because this product will give us the value of b here, that we have to show is equal to 0. So consider 1 over a into b. By using the associative property, we can write it as 1 over a into b. As these are the reciprocal of each other, this is equal to 1. 1 into b, 1 is a multiplicative identity, so this is equal to b. So this implies this product 1 over a into b, this is equal to b. Say this is the question number 1. Again we consider this product. Again we consider this product, or simply if we put the values of ab that is equal to 0 here, we simply put here 1 over a into 0, because a into b is equal to 0, this is given. So this gives b is equal to 0, that is required to prove. In the next paragraph, the author is describing about rational and irrational numbers. I hope you are familiar with the concept of rational and irrational number, their definitions. Now I am going to discuss a very important theorem, but it is a basic theorem that I hope you know from your college or school level. Theorem 2.1.4. In this theorem, we have to show there does not exist a rational number r such that r square is equal to 2. That is, there is no rational number r that whose square is a 2. Whose square is a 2. Theorem 2.1.4. In this theorem, we have to show that there does not exist any rational R such that R square is equal to 2. Prove. We suppose on the contrary that there exists a rational number R whose square is 2. We suppose on the contrary that there exists a rational R such that R is equal to P over Q, where R is in its lowest form. In other words, we can say that P and Q have no common factor between them. And more concisely, we can say that their GCD, this bracket shows the GCD of PQ, greatest common divisor. GCD of P and Q is 1. Mean to say P and Q have no common factor between them except 1. So there is a rational number R is equal to P over Q that satisfies R square is equal to 2. So plug in this value of R, that is P over Q, in the original equation. We have okay, substituting this value of R, P, that is P over Q, in the equation R square is equal to 2, we have P over Q whole square is equal to 2, which is equal to P square is equal to 2Q square. If you see on the right side, this is a 2Q square, that is that shows it is an even number or it is a multiple of 2. This implies P square is even because the right side is even. If you put any value of Q is an integer. Suppose Q is 1, this is 2. Q is 2, this gives us 8. So for any value of Q, this side is an integer. So this shows that P square is an even integer. So P square is even, this implies P is even. If the square of a number is even, then it must be that the number is also even, is itself even. So we suppose, because P is even, let P is equal to 2m and m is an integer. So plugging this value of P is equal to 2m here, put in 1. Put in 1. 1 implies 2m whole square is equal to 2q square. This implies 4m square is equal to 2q square. This implies q square is equal to 2m square. Similarly, as above, here again this number 2m square is an even integer for any value of m. So finally q square is an even integer. From here q square is an even integer. If q square is even, then it must be that q is itself even. So from here, this shows that both p and q are even. It means they have a common factor 2. This implies p and q both are even. It means their GCD is 2. That contradict with our assumption. That contradicts with our assumption, because we have assumed that their GCD is 1. Now we have proved that their GCD is 2. So it contradicts with our assumption. Hence, our supposition is wrong. Our supposition that R is a rational that satisfies R square equal to 2 is wrong. Hence, finally, we will say there does not exist any rational number whose square is 2. Okay. Next, I am going to discuss the most important and the most important concept that can we say this is a backbone of this chapter, the order properties of R. Actually, the order properties of R shows the relationship between the two real numbers. So, firstly, I will give here a basic definition. Order properties of R. Firstly, I am defining set of positive real number p. Let p, this p, is a non-empty set, and subset of R is a set of positive real number, is a set of positive real numbers that satisfy the following axioms. Throughout this chapter, when we will discuss a set of positive real number, we will denote that set by this p. Now this p satisfied the following axioms. The first axiom is that is actually the Collier law. For all a, b belong to p, if a and b are the two positive real number, then this implies their sum also belong to p. Mean to say, if a and b both are greater than 0, this implies their sum a plus b is also greater than 0. This is the Collier law of with respect to addition. Okay. Next one is the Collier law with respect to multiplication. In multiplication, we say that if a and b are the two real numbers from p, this implies their product a into b also belong to p. And the last one, the third property that satisfied p, if A is any real number, then exactly one of the following hold. Then exactly one of the following hold. The following hold. Either A is equal to 0 or A is non-zero. If A is non-zero, this shows A is greater than 0 or A is less than 0. So, we can express this property in the set of P as if A is greater than 0, this shows that A is an element of P. But if A is less than 0, it means minus A is greater than 0. In case when A is negative, then minus A clearly positive. This shows minus A is an element of P. And this property is called trichotomy property. Trichotomy property. Because in trichotomy, in trichotomy property says that if A and B are any two real numbers, then either they are equal or they are not equal. If they are not equal, then it shows either A is greater than B or A is less than B. So in this, and the third property, we are comparing A and 0. So in this property, our B is 0. So if you choose any A belong to R, then it is possible either it is equal to 0 or this is a non-zero. If it is non-zero, then it consists on these two parts. Uh, it may be positive or negative. But in both cases, it belongs to P if it is positive, and in case it is negative, then minus A belongs to P. The next one is 2.1.6 definition. In the definition, we define the inequalities between the real numbers in terms of set P. The next one is the definition 2.1.6. Definition 2.1.6. This definition says let A and B are the two real numbers. If A minus B belong to P, then A is greater than B. How this is possible? As you know, P is a set of positive real number. This shows this number A minus B is positive. By adding B on both sides, this gives A is greater than B or B is less than A. And in the case of non-negative real numbers, the second one is if A minus B belong to P union 0. P union 0 means this is a set of non-negative real number. In this case, A is greater than or equal to B. Next, we discuss the rules of inequalities and illustrate how the basic order properties are used to derive these rules. Theorem 2.1.7. These are the rules of inequalities. Okay, these rules of inequality are actually the order properties of R. In these order axioms, Theorem 2.1.7 1.7. This theorem says that let A, B, C are real number. Let A, B, C are the real numbers. In the first part, we show that if A is greater than B and B is greater than C, this implies A is greater than C. This is the transitive property actually. Given A is greater than B, this shows that A minus B is positive. A minus B is greater than 0. If A minus B is greater than 0, it means A minus B is positive. This implies A minus B is an element of set P. Similarly, if we consider the second inequality, B is greater than C implies B minus C is greater than 0. This shows that B minus C belong to P. I have to show that A is greater than C. How can we show this? We will show that A minus C is greater than 0, and this is possible that A minus C belong to P. So, if A minus B is greater than 0, it means A minus B is belong to P and B minus C is also belong to P. In the definition of set of positive real number, we have seen that the set of positive real number P satisfied the Hillier property. Mean to say, if we have a two positive real number, then their sum is also a positive real number. If A and B belong to P, then A plus B is also belong to P. So these are the two real number, A minus B, this is also positive, and B minus C, this is also positive. Both the numbers belong to set of positive real numbers, so their sum is also positive real number. Their sum A minus B plus B minus C, this sum also belong to P because P is closed under addition, but this is equal to A minus B plus B minus C, which is equal to A minus C belong to P. This shows that A minus C is greater than 0. We can simply prove this alternatively without the concept of the, or without using the term P. As A minus B, this is a positive, and B minus C, this is a positive. So the sum of two positive number is positive. This shows that A minus C is positive. And A minus C is positive means A is greater than C. The next, in the B part, we have to show if A is greater than B, then by adding a C on both sides, A plus C is greater than B plus C. I hope you can do this part by yourself. By just considering A greater than B means A minus B is positive. Here we have to show that A plus C minus B plus C, that this difference, A plus C minus B plus C, this difference is positive. So when you add or subtract here C, you can reach at this step. I hope you can do this. In the C part of this theorem, we have to show that if A is greater than B and C is also positive real number, then if we multiply C, the sign of inequality will not change, and AC is greater than BC. Given A is greater than B, this implies A minus B is positive. This implies A minus B is an element of set P. Also, given C is greater than 0, this shows that C is positive. This implies C belongs to P. This shows A minus B and C both are the elements of P, and P is closed under multiplication, so their product, this product A minus B into C also belongs to P. As P is closed under multiplication, so this shows that this product C into A minus B also belongs to P. What is this product? This product is simply equal to C into A minus C into B, which is greater than 0, because this product belongs to set P. Or in other words, we can say that CA is greater than CB, or AC is greater than BC. That is required. Similarly, in case when C is negative, its second part is, if C is less than 0, then we have to show that AC is less than BC. In this case, the sign of inequality will change. As C is less than 0, it means C is a negative number. This shows that minus C is greater than 0. This implies minus C is a element of P. So as minus C is also belong to P, so by again using the Hillier property under multiplication, this product minus C into A minus B, this product also belong to P. What is this product? This product is simply equal to minus C into A minus minus plus C into B. This should be greater than 0 because this belongs to set P. This shows C into B is greater than C into A, or we can simply say that BC is greater than AC. That is required. Next one is a very important theorem, theorem 2.1.8. In this theorem, we have to show that if A is any real number such that A is a non-zero, then its scale is greater than 0. Very important theorem. In this theorem, we have to show theorem 2.1.8. In this theorem, we have to show that if A is any positive real number, A is any real number such that A is non-zero, then show that its scale is greater than 0. Okay. This is its first part. Given A is non-zero. As A is non-zero, it means either A is greater than 0 or it is less than 0. From this, we have two cases. Either A is greater than 0 or A is less than 0. Firstly, we consider the first case, case number 1. When A is greater than 0. When A is greater than 0, it means A is positive. A is positive means A belongs to set of positive real number P. This shows A belongs to P. If A belongs to P, then it is clear that P is closed under multiplication. So as P is closed under multiplication, this implies A square is equal to A into A belong to P. their multiplication belong to P, this shows that A square belong to P. It means A square is greater than 0. A square is positive because P consists on all those elements which are positive. When you say A square belong to P, it means A square is positive. Case number 2, when A is negative. Case number 2. When A is less than 0. A is less than 0, it means minus A is greater than 0. Minus A is greater than 0 means minus A is positive. This implies minus A belong to P. As P is closed under multiplication, this shows that the product A square is equal to minus A into minus A. This gives us A square. And both these are the elements of P, so their multiplication also belong to P. This shows that A square belong to P, implies A square is greater than 0. So in both cases, either A is positive or negative, their square is always greater than 0 in case when A is non-zero. In the B part, we have to show that 1 greater than 0. It's in its B part, we have to show its B part. In its B part, we have to show that 1 is greater than 0. As 1 is a real number. I will use its A part. A part says if A is any real number, so 1 is a real number. Further, that real number should be non-zero. It is clear that 1 is non-zero. Then its square will always greater than 0. This implies its square is always greater than 0, but its square is equal to 1 because 1 square is equal to 1, so 1 is positive. Simple. And it's in C part. If n is any natural number, then n is greater than 0. Its C part says if n is any natural number, then we have to show that n is greater than 0. We will prove this by induction, mathematical induction. Assertion is true. Assertion means statement, claim. Assertion is true for n is equal to 1. In the B part, we have shown that 1 is greater than 0. So in mathematical induction, you know, it consists on 3 steps. First, we prove the statement is true for n is equal to 1. For n is equal to k, we assumed, and for n is equal to k plus 1, we show. So assertion is true for n is equal to 1 mean this is by part B. By B. Part B. We suppose the statement is true for n is equal to k. We suppose statement is true for n equal to k. This implies k is greater than 0. Mean to say k belong to P. As 1 is positive, 1 is greater than 0, k is also positive. As 1 and k both belong to P, this shows their sum 1 plus k is also belong to P by using Hillier law of addition with respect to Hillier property of addition for P. If 1 plus k belong to P, this shows 1 plus k is positive. So the statement, this shows this statement is true for n is equal to k. Statement is true for n is equal to k plus 1. Hence, by mathematical induction, we can say that statement is true for every positive integer. And this completes the proof. The next one. Okay, next I am sharing an important thing just for your knowledge. As you know, if a real number a is greater than 0, this is called the positive real number. Can you tell me which is the smallest positive real number? Can you find a positive real number a that is the smallest one? Yes. Suppose someone say 0.0001. This is the smallest positive real number. Suppose I can find another real number that is 0.tetra01. This is smaller than the previous one. Or the simply, if I half this, the next number will be smallest this. And if I continuously continue this process, every time I half the answer, the next one will always smaller the previous. So we cannot find the smallest real number. So we have a result. There does not exist a smallest positive real number. There does not exist a smallest positive real number in R. It can be followed as if a is greater than 0, then clearly as 1 by 2 is also greater than 0, that is positive. This implies 1 by 2 into a is also greater than 0. As this can be written as 0 less than half a, and half a is always less than a. So we can find a real number that is half of a between 0 and a. So I cannot claim that a is the smallest positive real number. So again, continuing this process, I can again find a positive real number between 0 and half a, that is 1 by 4a. So there does not exist the smallest positive real number in R. Next, I am going to discuss a theorem 2.1.9 that have the same scenario as this fact. If a is any real number such that 0 less than or equal to a and a is less than epsilon, where epsilon, for every epsilon greater than 0, then a is equal to 0. Theorem 2.1.9 says, Theorem 2.1.9 says, if a is greater than 0, a belong to R, and 0 less than equal to a is less than epsilon, for every epsilon greater than 0, this implies this is only possible when a is 0. We prove this result by contradiction. We suppose on contrarily, that a is exactly greater than 0. A is exactly greater than 0. This implies I can find an epsilon naught such that this is equal to half a, which will be greater than 0. This shows that this result shows that we can write 0 is less than half a. In other words, this is equal to epsilon naught, which is less than a. But this contradicts with the fact that a is less than epsilon for every positive real number epsilon. And here epsilon naught is also positive. But this contradict with the fact that a is less than epsilon for all epsilon greater than 0. Because here we find an epsilon naught which is less than a. Hence our assumption is wrong. A is less than or equal to 0. So our assumption is wrong. This shows that a is equal to 0. We will use this result frequently in our incoming lectures, in continuity, in Riemann integration. You will see you have an expression 0 less than equal to some definite number, a definite integral a to b f of x dx, and this is less than all positive real number epsilon, where epsilon is greater than 0. From this expression, we will always conclude that this integral is exactly equal to 0. Because in this expression, our integral is playing the role of a. Okay. Next, there is a theorem 2.1.10 that is actually the positivity of the product. In this theorem, we have to show if the product AB is positive, then it is possible only when both A and B are positive, or either both are negative. And similarly, this theorem has a corollary in which the product AB is negative, and we have to show that this is possible when either A is less than 0 and B is greater than 0, or A is greater than 0 and B is less than 0. So I am not proving this theorem here, and this is your assignment. I hope you can do this. Otherwise, I will share this proof of this theorem in description box. The next one is the inequality. These are the simple numerical examples. 2.1.12. 2.1.12 we have some inequalities that we have to solve. Actually, in this example, we have to show that how we will use the order properties to solve the inequalities. So first one is 2.1.12. This is determine the set A of all real number x that satisfy the inequality 2x plus 3 less than 6. The solution set of this inequality is denoted by A. This is very simple. By adding the additive inverse of 3 on both sides, we have 2x less than 6 minus 3. This is 2x less than 3. Now by multiply the multiplicative inverse or the reciprocal of 2 on both sides, this gives 1 by 2 into 2x less than 1 by 2 into 3. This is 1, x is less than 3 by 2. So your solution set A is simply set of all real numbers such that x is less than 3 by 2. Simple. And in the example, there is an equal sign also here. Next one, it's B part. In the B part, we have a set B that consists on set x belong to R such that the expression x square plus x is greater than 2. X square plus x is greater than 2. Here we will use the theorem 2.1.10. Firstly, consider this equation, quadratic equation. We make the factor of this equation. This is x square plus 2x minus 2 is equal to 0. X plus 2 minus 1x plus 2 equal to 0. This is x minus 1 into x plus 2 equal to 0. So I can write this inequality x square plus x minus 2 is greater than 0, and the left side can be written as the product of the two factors. Theorem 2.1.10. Theorem, by using theorem 2.1.10, says that the product AB is positive if either both are positive or both are negative. Both the numbers have the same sign, in other words. So we will consider from here the two cases. Case number 1. Case number 1. When both of the factors are positive, when x minus 1 is greater than 0 and x plus 2 is also greater than 0. From here, by adding additive inverse of 1 on both sides, this greater than x greater than 1, and from here x is greater than minus 2. Now we find the common values between both of the solution, x greater than 1 and x minus 2. This can be done by drawing a real line here, minus infinity to positive infinity. This is my x equal to 1, and suppose this is my x is equal to minus 2. This shows x is greater than 1, but 1 is not included, so this is x greater than 1. This region shows x greater than 1, and this is x greater than minus 2. So this is x greater than minus 2. Now the common values between both of the arrows, you can see this area is the common region that satisfies both of the inequalities. For example, if you pick a number from here, from this region, suppose x is equal to 0. If you put x is equal to 0 in the first inequality, suppose here 0 is bigger than 1. Is it true? This is not true, because this is not admissible value, acceptable value. So the only acceptable values are x greater than 1. So common values are x greater than 1. Next, we move towards the second case, when both of the factors are negative. Both of the factors are negative. Case number 2. When both of the factors mean x minus 1 is less than 0 as well as x plus 2 is less than 0. From here x is less than 1, and from here x is less than minus 2. Again we can draw the number line. This is x is equal to minus 2, and this is x is equal to 1. This shows x is less than 1, So this is the area that show these are the values that in which x is less than 1, and these are the values that shows x less than minus 2. The common values are clearly these. The common values are x less than minus 2. So by combining both of the cases, the solution set of this inequality is x belong to R solution set x belong to R such that x is less than minus 2 union x belong to R such that x is greater than 1. So these are the common value or the value of solution set B. Similarly, this example has a C part. And I hope you can solve that part by yourself. Now I am moving the last, yes, the next is example 2.1.13. This is also an important example. In this example, okay, next I'm going to discuss B part of example 2.1.13. The solution of A part I will share in the description box. This is important inequality, arithmetic geometric mean inequality. Firstly, we define arithmetic and geometric mean. If A and B are two positive real numbers, then their arithmetic mean is simply given by A plus B over 2, and their geometric mean is simply given by the square root of AB. This inequality is called the arithmetic geometric mean inequality. This inequality says if A and B okay, this inequality says that if A and B are any two positive real number, then square root of AB is less than or equal to half of A plus B. In other words, this inequality can be written as the geometric mean is always less than or equal to arithmetic mean. And the equality occurring if and only if A is equal to B. In case when A and B are equal, then arithmetic mean and geometric mean are equal. We prove this inequality for a positive real number, but for a distinct. Proof for A, B greater than 0, we suppose that A is not equal to B, and we show that the arithmetic geometric mean to say square root AB is less than the arithmetic mean. Okay. As we have assumed that A is not equal to B, this implies A minus B is not equal to 0. By using the theorem, 2.1.8, think, yes, 2.1.8a part, which says that if a is any real number such that a is non-zero, this implies its square is greater than 0. So according to this result here, the a and b are the real numbers. So a minus b is also a real number, and it is a non-zero number, a minus b. So according to this theorem, the difference a minus b is greater than square of the difference a minus b whole square should be greater than, just a minute. From here, I should involve the square root sign. As a is not equal to b, this implies square root a is not equal to square root b. And also, as a and b both are positive, so square root a and square root b also positive. This implies the difference square root a minus square root b is non-zero. By using the theorem 2.1a, now I can write it as square root a minus square root b is greater than 0, sorry. Now by expanding the square, we have a minus 2 square root ab plus b greater than 0, and from here a plus b is greater than 2 times square root of ab, and this can be written as square root ab is less than half of a plus b. That is required to prove. Next we show the equality sign hold. If a is equal to b, then both sides of star equal to a. If you put here a is equal to b in star, the left side is a square and the right side is 2a. So both are equal to a. So the equality hold in case when a is equal to b, both equal to a. This implies in this case square root ab is equal to half of a plus b. Conversely, we show that this equality, the arithmetic mean and geometric mean are equal, and we show that the numbers a and b are equal. Conversely, no. Conversely, we suppose that this expression geometric mean is equal to the arithmetic mean, and we show the number a and b are equal. So we just solve this equation, multiply by 2 on both sides. This gives us 2 into square root ab is equal to a plus b. By squaring on both sides, this gives us 4 into ab. This is equal to a plus a square plus b square plus 2ab. By subtracting 4ab from this side, we have minus 2ab is equal to 0. This is a minus b whole square equal to 0. This implies the square of a number is 0. It means the number is itself 0. This implies a is equal to b. That is required to prove. So this is the arithmetic geometric mean inequality for any two positive real numbers. We can generalize this inequality. The most general form or generalized arithmetic mean geometric mean inequality is General arithmetic geometric mean inequality. Suppose that A1, A2, A3 up to so on An are positive real numbers, then the geometric mean in this case is A1 into A2 into An. This represents the geometric mean uh, of the product of n positive real number. When we have a two positive real number, then the geometric mean is just the square root of AB. Suppose we have a three positive real number, then their geometric mean will be the cube root of the product of three real numbers. In case when we have n positive real number, then their geometric mean is simply the nth root of their product. This is less than or equal to a1, a2 up to so on an this over n. This is the arithmetic mean of n positive real numbers. The equality will occurring if all of these numbers are equals. You can prove this inequality, general arithmetic geometric mean inequality, by using mathematical induction. But inshallah we will discuss this inequality in chapter number 8. Because by using mathematical induction it becomes tedious to prove this theorem, this inequality. Next I am going to discuss the last topic of today's lecture, that is the Bernoulli inequality. Okay, to prove Bernoulli inequality, that can be stated as if x is any real number which is greater than -1, then 1 plus x raised to power n is greater than or equal to 1 plus nx. To prove this inequality, we use mathematical induction. It is clear that for n is equal to 1, the assertion is true. Suppose if you put here n is equal to 1, and on the right side if you put n is equal to 1 here, both are equal because this is also 1 plus x. So the statement is true for n is equal to 1. Just for your knowledge or your information, but there is no need to do this in question paper. For n is equal to 2, if you solve this inequality for n is equal to 2 here, this gives us 1 plus x square, and on the right side this is 1 plus x square. This gives us 1 plus x square plus 2x, or 1 plus 2x plus x square. As x is greater than -1, this implies its square will always positive. So it means this number, the third number x square, is a positive. If we leave this number, then the left side 1 plus x square, which is actually the sum of these three, will always greater than 1 plus 2x. This shows that the inequality is also hold for n is equal to 2. For n is equal to k, suppose that the statement is true for n is equal to k, then it means 1 plus x whole power k is greater than 1 plus kx, where k is a natural number. Suppose this is my equation, inequality number 1. I will show that the statement is also true for n is equal to k plus 1. The statement for n is equal to k plus 1 is, I have to show this should be greater than or equal to, this should be greater than or equal to 1 plus k plus 1 into x. We solve the left hand side, we take the left hand side and show that this is greater than or equal to this number 1 plus x raised to power k plus 1. Can we break this as 1 plus x into k into 1 plus x by using 1? By using 1 as 1 as in 1 plus x whole power k is greater than or equal to 1 plus kx. So when we multiply this number 1 plus x in 1, if you multiply 1 plus x in 1, then we have 1 plus x whole power k into 1 plus x. This is greater than 1 plus kx into 1 plus x. So this product is greater than or equal to this number. So I can replace this by 1 plus kx into 1 plus x. Multiply these two factors, we have 1 plus x plus kx plus ax square. By taking x common from here, this is 1 plus x into k plus 1, 1 plus kx square. As x is greater than minus 1, this implies x square is greater than 0. As k is any natural number, this shows kx square is, so k is, as k is any natural number, so k would be greater than 0 also. This shows that this product is also positive. So if we left this the third number, this gives us 1 plus x whole power k plus 1 is greater than or equal to 1 plus x into k plus 1. Okay, so I hope and I can hope you have a now clear understanding of today's long lecture. So if you find any difficulty, any query in this lecture, you can comments me, inshallah I will reply you. So in next lecture we will discuss properly exercise 2.1. If you find my lectures are helpful for you, kindly like, share and subscribe my channel. So see you in the next lecture. Take care. Allah Hafiz.